And today we are supposed to be discussing the reactions between epoxide with nucleophiles in the absence of acid catalyst. So the first, why epoxide is unusually reactive in comparison with other ethers is because epoxide features very large angle strength. Okay, so this epoxide ring has the bond angle of 60 degrees, but it wanted a bond angle for sp3 hybridized atoms, two carbons and oxygen supposed to be 110 degrees. So it's 50 degrees difference, okay, in the actual bond angle and the desired bond angle makes the epoxide, ring highly likely to participate in the reaction. And also it has the, the two carbons being, the electrophilic. So bunch of nucleophiles can react with, those ring carbons, and this lead to ring opening reaction. But the requirement for this nucleophile is the nucleophile generally must be nucleophilic enough. So the rule of thumb is you want the nucleophiles at least about 1,000 times more nucleophilic than water or alcohol. So neutral water or alcohol is something I would like to recall you learning Organic 1 Chapter 6. The nucleophilicity of neutral water or alcohol is usually treated as a reference nucleophile. Have nucleophilicity of 1. Okay, so if you want a those nucleophiles, water, alcohol, their nucleophilicity is too weak to react with epoxide. You need a nucleophile that is usually about at least 1,000 times more nucleophilic than neutral water and alcohol. So what are examples of such, the highly nucleophilic nucleophiles? The best kind of nucleophile we can find normally is the thiolate, okay? The conjugate base of thiol, they are extremely nucleophilic. Then something else, the alkoxide and the hydroxide, they're about 100 times less nucleophilic than thiolate, but still is about 10,000 times more nucleophilic than neutral water or alcohol. And then all the halides, they are also, the about 1,000 to 10,000 times more nucleophilic than, the neutral water or alcohol. And something else is ammonia has a lone pair, and the amines, they also have nitrogen lone pair, azide, and the cyanide ion. Those are examples of highly nucleophilic nucleophiles that can react with epoxide. Obviously, there's one kind of nucleophile we just learned is the carbon anion, the Grignard organolithium that we just you just had a test. You learned in the test, okay? That thing, Grignard or organolithium can react with epoxide. So this reaction in general, depending on what kind of nucleophile you use. So if it's a Grignard, okay, or organolithium, you always have to do a two-step reaction. So you have to mix the Grignard, okay, or organolithium with this ethylene oxide or other epoxide in THF or diethyl ether. Then second step, add acid. That's just like a standard. Okay, but for thiolate, alkoxide, hydroxide, you could directly carry out the reaction in the protonic protic solvent, like in case of this thiolate. Okay, You can direct carry out the reaction in water or ethanol water, the mixture. The reason chemists use the ethanol water as a mixture is basically because of if pure water, the solubility of this thing may be a little bit, for the ethylene oxide, maybe a little issue. Okay, so there is ethanol water for better solubility. So the reaction mechanism, we can follow the general mechanism. If you have a nucleophile, okay, if the nucleophile is powerful enough, it can react with the ring, give you the attack the ring carbon, then give you the alkoxide ion, okay? And then this alkoxide ion either can accept the proton from a reagent added in second step. That is, the what happened when the nucleophile, okay, is organolithium or Grignard, okay, basically second step, okay, or if it's the less basic nucleophiles like thiolate, alkoxide. Those solid alkoxide, because they are not overly basic, they can work with a protic solvent. So you can directly, the react in protic solvent. For instance, if you want using methoxide, okay, ethoxide, okay, you want to react with this one, you can do it in ethanol as a solvent because, well, this base even react with ethanol, it will still provide, will convert ethanol to ethoxide and itself become ethanol. So there's no total change in composition. Okay, so but the ethanol can serve as a proton donor. It will give you this product. Okay, so the this O, okay, we're attacking here, okay, and then this one will break. Carbon oxide one will break, and that is I hope you remember we discussed last class why carbon oxygen one breaks, because of the by breaking carbon oxygen bond you can generate better leaving group. Okay, so this is when the epoxide, okay, is when the epoxide is just ethylene oxide, okay, or the if the epoxide has the ring carbons have equivalent substitution. Like in this case, both the ring carbons, they are secondary carbons, okay? Both ring carbons, yeah. So this is secondary, okay? This also secondary. So it doesn't matter which ring carbon to attack, you will have the same product, okay? But this attack, okay, always is SN2 type attack. So if we look at let me just draw it here. That was a 5-member ring. So if we have a 5-member ring here, let's say we have this epoxide, okay? And then if we have this one as a nucleophile, okay? So that this nucleophile assume attack from the top face, okay? Because of we are showing the carbon oxygen bond, okay? That connect to the ring below the ring plane. Okay, that's what the dash bond shows. Okay, so then this carbon oxygen bond, okay, the nucleophile, okay, must attack the electrophilic carbon from the opposite side of leaving group. Okay, so that lead to one possible product. So this CO bond, okay, must attack from the opposite of the leaving group, and this one is a leaving group. Okay, so you attack from the top face of the ring, above the ring. Okay, because the CO bond is connect to this carbon from the below the ring direction. Okay, so if the attack always SN2 attack, so this one gonna attack from the top face of the ring. Okay, so then what you will see is the left side ring remain intact. Okay, and then the so that is one of the possible products. Okay, so if you attack the other, you will pretty much will see very similar product. If you technically also can attack here. Okay, if attack here, then this one breaks. Okay, then what kind of product you'll be getting? You're getting this one. Both are the the trans product. Okay, both are trans products. You see the SOC group and the OH group, they are trans to each other. Okay? So that is a result of SN2 type attack. So this is a common feature for every reaction with epoxide. Okay? The nucleophile always attack from the opposite side of the breaking carbon oxygen bond. Always. So the attack always SN2 type attack. Now that is relatively simple as long as you know the attack will be SN2 type. Okay, but in some situations, like we see here, the two ring carbons, okay, they are not equally substituted. As you can see here, one carbon is a secondary carbon, and the other carbon is a tertiary carbon. So here, the nucleophile will have to choose, obviously the nucleophile will attack one of the ring carbons faster than the other, okay? Because the two carbons are non-equivalent, okay? But which one will be attacked faster? So because this is SN2 type of attack, we know SN2 type of attack, what is the most sensitive thing for a given nucleophile? What is the most sensitive factor to affect SN2 reactivation? Stereohydrins as the electrophilic carbon. Okay, so if no other factors, play to the role. Okay? So obviously tertiary carbon has a much larger stereohydrins than the secondary carbon. So when the nucleophilic SN2 type of nucleophilic attack happens in the absence of acid catalyst. That's important. In the absence, okay, of acid catalyst, then the nucleophile will always attack the less substituted carbon, because after all, it's SN2 type of attack, and the less substituted carbon will have a less stereohydrins. So the attack on the left side of carbon will be faster than on the right side of carbon, because the left side of carbon is a secondary carbon, and the right side of carbon is tertiary carbon. Okay? So now, let me just draw here to show you what exactly happened. So sodium ethoxide, just for the sake of simplicity, we can use the net ionic equation, just represented as methoxide ion. Okay, so the nucleophile will be attacking the left substituted carbon. Okay, and this attack still will be SN2 type attack. So the attack will happen along the direction that is opposite to the breaking bond connecting the electrophilic carbon and the leaving group. So this bond, okay, will be breaking, okay, because we know we'll be attacking this carbon, right? Can you see my dot? Okay, this carbon. So it will be coming from the opposite side of leaving group. Okay, and then this one breaks. Okay, so that will give you as the the product of this single step. Okay, you will have the methoxy group. Okay, bound to this carbon. So let me color code it. This carbon, okay, is this carbon. And then the right side carbon is not being attacked, okay? So there's no change, okay, on the right side carbon. So then, so this oxygen is this oxygen, okay? So that is the product of the SN2 type of attack, which is alkoxide, okay? Then this alkoxide, okay, can take a proton from methanol. Here is a solvent, methanol. Take a proton, okay? Give you the final product showing here, okay? Any questions about this nucleophilic attack? No? Okay. So we can look at a few more examples, okay? Say we have this epoxide, and let's say we let it react with ammonia, okay? So say the reaction happened just in water, okay? So the first, when you look at this type of reaction, first thing you want to expect, oh, is any acid catalyst there, okay? Obviously, ammonia is a weakly basic, I assume you guys know, okay? So we don't have acid catalyst. So the environment is basic. You don't need to think about acid catalysis. So then the ammonia is a nucleophile. It will attack which carbon will be attacked faster. Attack will be SN2 type. Is the green carbon or the blue carbon? Green, because that's less steric hindrance. Okay, so that the nucleophile comes from opposite side of leaving group. Okay, and then break the CO bond to the less substitute carbon. So this will give you H3N. And just keep all the formal charges. Make sure you have correct formal charges. Okay, so I'm just circle the carbons. Okay, so keep track. Help you keep track of them. The blue one will change. The green one will be attacked by the ammonia. Then the proton transfer. See, this guy gonna lose a proton to here, so we can say, oh, this we can draw a few protons. So this guy can take a proton away from the nitrogen atom. You will get the product. Again, I will circle it. Okay. Okay. Next example, let's say we have a specific, say, okay, we have this epoxide. Okay, it's chiral and optically active. Okay? So now, if we allow this guy to react with a combination, say, of this, say, okay, the solvent, okay. First thing, again, check whether there's any acid catalyst there. Okay. No, okay. Then look at what is the most powerful nucleophile in the system. What is the most powerful nucleophile in the system? It's the thiolate, okay? So this one is the most powerful nucleophile, okay? So this is thiolate. And then in this case, we will see, oh, where the, the nucleophile will be attacking the two carbons, okay? Red is electrophilic, blue also is electrophilic. Then which one is being attacked? Because there's no acid catalyst, so whatever has necessary hindrance will be attacked. So the red carbon will be attacked. So then the nucleophile will be attacking from the opposite side of the leaving group. Okay, so basically, we will take the nucleophile, okay, from opposite side of leaving group, okay, attack here, okay, and break this one. So what we do is, we're gonna see, oh, nucleophile will attached to this ring carbon. That's originally carries red circle. That's a ring carbon, okay? Original ring carbon, okay? And then the other ring carbon, okay? There's no change. The blue one, there's no change here, okay? And then you're gonna have a configuration inversion here. And then obviously, this guy can get the proton, will give you the final product. Okay, so you must because SN2 attack always a configuration inversion at the site of attack. So if you can find what is the sign of this one, this is what sign? Oh no, this is okay. This was this R. After attack will be S. Okay. The last from SN. Yeah. Well, that's the only source, right? There's no other possible source, okay? All right, so that is a reaction if without the catalyst, okay? Without catalyst, usually you need a powerful nucleophile because after all it's a neutral ether, okay? It's the reaction is kind of slow, okay? So now if you're adding acid, the ether can react with the nucleophile. The epoxide can react with nucleophile substantially faster, and this is actually for the same reason as we have seen why acid can catalyze cleavage of ether. That we discussed last class. If HBr or HI, it can cleave regular ether, not even epoxide. That's a conventional ether. HBr, HI can cleave a regular ether because after protonation, okay, ether oxygen can be easily protonated. Then you're going to have a better leaving group. because you break this bond, become if you after protonation, if you break one of those carbon-oxygen bond, you are forming a neutral alcohol as a leaving group. And a neutral alcohol you can treat just the same as water. They are excellent living groups. Neutral alcohol and water, they have comparable living group quality. I'm not saying they have exactly the same, but a comparable living group quality. So if after protonation, then if you break this bond, you're gonna generate a neutral alcohol as a living group, right? So much better living group. And also after protonation, you have a greater positive charge on those two electrophilic carbons. That makes the two carbons more electrophilic. So that's why an acid can serve as a catalyst, okay, in epoxide reaction with a nucleophile. So typical acid catalyzed reaction between epoxide and the nucleophile is when the nucleophile is weak, like neutral alcohol, water. Okay? Those are typical examples. Because if the nucleophile is strong, you don't need acid to catalyze. Okay? And keep in mind, when the nuclear, if you add acid, you have the possibility to combine with an ionic nucleophile, make it less nucleophilic. Okay? So if the nucleophile is strong, you don't need acid to catalyze, and you potentially could occur the nucleophilicity of nucleophile. Okay? So under what situation you need acid catalysis in terms of reaction between the epoxide and the nucleophile is when the nucleophile is neutral nucleophile, like alcohol or water. Okay. So now in this case, that's just one example. If you have ethanol react with ethylene oxide, if you don't have a catalyst, this reaction is extremely slow. Okay, it may take months to complete. But if you add a sulfuric acid, the reaction can happen really fast. Okay, and can give you the 2-ethoxyethanol as a product. Okay, and mechanistically, the reaction, involves the protonated epoxide as a real electrophile react with nucleophile. So when the alcohol, when the nucleophile react with the protonated epoxide, the nucleophilic attack still is SN2 type, still with the inversion of configuration. And why the reaction happens this way? Because of it is faster in this epoxide the reactions. Okay, so we can look at compare what are the potential energy diagram for a regular ether, like if you have this ether. Okay, if you want to react with say HBr. Okay, if this reaction happens, the first step is always a protonation, okay, of the ether, and then in this case the ether, the proton ether can undergo two possible pathways. One is SN1 pathway. It forms a tertiary carbocation and a neutral methanol. The other one is SN2 pathway. The bromide ion directly attacks here. Okay, you will get to get to alcohol. Okay, so there's no clear, the rules state which path will be faster. So both paths might be feasible. That is because of the this protonated ether, it has a relative low potential energy. So the both SN2 and SN1, they have a similar rate, okay. But in case of epoxide, okay, let's say you have this epoxide. If we react with HBr, okay, and then it will be protonated just like regular ether. And then in this case, the bromide ion, okay, will attack, okay, basically here there's two possible options, okay. One is you can think about, okay, the breaking up into carbocation first. If this one breaks up, okay, become carbocation, the other path is directly, the nucleophilic attack. Say, attack here, okay? So the because of this guy, okay, has a substantially, the lower, substantially higher potential energy than this one. This guy, okay, has substantially higher potential energy than this guy because of the inherent angle strength. So it makes the the SN2 attack actually it's faster. Okay, so than the regular ethers. Okay, so that lead to interesting the result is that although if in most of the cases we have seen in organic one, if you have acid catalyst in a reaction, it often lead to a carbocation. Okay? But in this particular case, epoxide, if you use acid catalyst, the reaction does not involve a carbocation. Yet, okay, if you have the when the the two ring carbons, they have different degree of substitution. The nucleophile, okay, will attack the more substituted carbon. Okay. So what does that mean? If we look at this particular the epoxide as example, you have two the potential electrophilic carbons. Okay, one is a tertiary carbon, the other is secondary carbon. And then, as we know, the reaction, because the reaction catalyzed by sulfuric acid, the first step is the ether oxygen will be protonated. Then the nucleophile here is methanol. It will can selectively attack one of the two electrophilic carbon atoms. Although it's SN2 type of attack, okay, but in this particular case, because the transition state is of special kind of transition state, so this nucleophile actually will attack the more substituted carbon faster. Okay, so that will lead to this product. This one breaks. Okay. So let me just color code the the two potential electrophilic carbons. Okay, So help you keep track of them. So the nucleophile will be attacking the more, substitute carbon. Although configuration inversion is still involved here. Okay. So why the nucleophile would like to attack the more substitute carbon? You have to think about the transition state of such SN2 attack. We know that the transition state of SN2 attack is, both the incoming nucleophile, okay, is half bound to the electrophilic carbon, and the breaking bond from the electrophilic carbon to the the leaving group also the half bonded. Okay, so because the nucleophile, incoming nucleophile originally is neutral, and if partial bond form, that means this part of this lone pair is given to the electrophilic carbon. So the nucleophilic, that is oxygen, will carry a partial positive charge. At the same time, because of this bond also partially broken, so this central oxygen also carry a partial positive charge. And also the leaving oxygen also carry a partial positive charge. So that leads to an interesting transition state where the three atoms, the incoming nucleophilic atom, the electrophilic carbon, and the leaving group, okay, all of them share 1 unit of positive charge. So this gives this electrophilic carbon a partial carbocation character. It's not a full carbocation, a partial carbocation character. Okay, but if this is a partial carbocation character, you can consider the stability of this transition state is impacted by the degree of substitution at this carbon in a way that is very similar to a true carbocation. What is true carbocation? How the degree of substitution affect the true carbocation? Anyone recall? What is the degree of substitution impact the stability of true carbocation? Yes? Yeah, the more alkyl groups you have, more sp3 hybridized carbon you have on that positive charge carbon, make it more stable. The same argument can be applied here. If you have more alkyl carbon connect to this electrophilic carbon, will make it more stable. Okay, so now if you look at two possible transition states, so that is the transition state where the nucleophile attack the more substitute carbon. Okay. And this is transition state where the nucleophile attack a less substitute carbon. So which of those two, the electrophilic carbon is better stabilized? If you consider it has a partial carbocation character, and obviously I hope you can see this one has a 1, 2, 3 carbon bound to it. Okay? So this carbon can be treated in a similar way as a tertiary carbocation. Okay, but this one only have 1 and 2 carbon direct bond to it. So this one can be treated in a similar way as secondary carbocation. So that means if you compare these two transition states, the left side transition state is more stable. So if a transition state is more stable, what is the impact of reaction rate? If transition state is fast, okay, so that's why when a nucleophilic reaction between epoxide, if the nucleophile react with the epoxide is catalyzed by an acid, the nucleophile will be preferentially react with more substitute carbon because such a nucleophilic attack will lead to a more stable transition state. If the transition state is more stable, I'm not talking about final product being more stable. if the transition state is more stable, such a nucleophilic attack event will be faster. Okay, so that's why the when you have a the nucleophile react to epoxide and the two ring carbons, they are different substitute than the epoxide. Always going to react. But we have the more substitute ring carbon to react with with nucleophile. So just give example. If we have a sulfuric acid, okay, then this carbon will be attacked. So you're gonna have CH3O connect to here, okay. That is a product, okay. Connect to the more substitute carbon. But if you have a same epoxide, if you react with this, okay, that means you don't have acid catalyst. In this case, the nucleophile will be attacking the less substitute carbon. So this will be attacked. So you have CH3O attack, okay, this carbon, and then I hope you can see the difference. Okay, so the direct comparison, one is with the top one with acid catalyst, so nucleophile will be attacking more substitute carbon. The bottom one is without acid catalyst, so the nucleophile will be attacking the less substitute carbon. Okay, so I'm gonna stop here. I'm gonna see you guys next class. And if you haven't completed the survey, be sure to do it by 10. The survey will close at 10. And the survey result will decide, okay, how our class will be running, the between exam 2 and exam 3. And also the homework due today, if you haven't given me, be sure to submit online. Oh, thank you.
So you still drop one test, right?
Yeah.
For 15 and 23, we have to do the entirety of them since they're shorter, or just,
Oh, still 80%.
Still okay.
But you should have done the homework.
I do it, but I don't write it like for like to upload it.
Oh,
yeah,
okay.
I do it while I'm studying, but then like it's all over the place. So.
Oh, okay.